Okay, so you had three problems in your class on Monday, right? From Stone-Oyster's theorem. So mainly we will discuss on those three. So these are not that much easy to solve. So this needs some basic applications of there is something called Deni's theorem, so which you have learned, and of course the Stone-Oyster's theorem and all those. So the first problem was that question number 6 from page number 90. Of course, the book by Elepentus and Barkinshaw. So it tells that a polynomial is odd or even. So you have a polynomial px. So a polynomial is of the form, right, a0 plus a1x plus up to plus an x to the power n, right? Now these terms, let's say xi, so these terms are called monomial, and so these are called monomials. And if you see this one, say a1x, it is a monomial of degree 1. So this is a monomial part of degree 1. Similarly, this is a monomial part of degree n, and so on. Now we call a polynomial, say n degree polynomial, is an odd polynomial if it does not contain any monomial of even degree. Means in this polynomial p is odd if the terms consisting of this kind of say a to m x power 2m. So this kind of terms will not be present in the polynomial, including m equal to 0, means including the constant term. So we call a polynomial p to be an odd polynomial if there is no monomial of even degree. And similarly, we call it as an even polynomial if there is no monomial of odd degree, right? Now the question asked, show that a continuous function f which vanishes at 0. So a continuous function vanishes at 0 if and only if it is the uniform limit of a sequence of odd polynomials. Means if we have a function f, of course belongs to C01, then f0 is equal to 0 if and only if that there exists a sequence Pn of odd polynomials such that this limit norm Pn minus f is equal to 0, or this converges to 0. Fine. This is the question actually.
Fine, sir.
So okay, so let's discuss this problem. Okay, so rather than, because you are the only one present here, so let's discuss this problem. So what do you feel? Suppose that suppose there is a polynomial. First of all, what can you say about the polynomials if they are of odd degree? So if Pn is a polynomial of odd degree, sorry, odd polynomial, then what can you say? Its constant term is 0, right? So there is no constant term in this polynomial. Then what can you say about Pn 0?
0.
Yeah, this is equal to 0, right? Now suppose you have a polynomial of odd term, this kind of polynomials, and suppose this polynomial converges uniformly to a function f. Okay, this is uniform. So what is the distance function here? So this means supremum of mod Pnx minus fx, right? Such that here you can say x belongs to 0, 1. So this is the definition of, so What is norm infinity? See that quickly? This is
Supremum of fx.
supremum of
Fx.
supremum of x.
So for all x belonging to R or x belonging to x, supremum of f.
So तब क्या होगा if your function is like this? Here it is 0, here it is 1. If your function is this one, then what is norm? Then all the values are negative, right? Hmm? This is, you need a
So
modulus here, okay?
def. Yes, sir. Yes.
You need a modulus here. So actually, in during the interviews, this kind of questions they basically ask, like some basic questions. They will not ask you very difficult on all those. So whenever you go for some PhD interview, you will face this kind of problems. Okay. So you have this one. So you also know that whenever a sequence of function converges uniformly to another sequence, then it also converges pointwise, right? So since this converges is uniform, so what we can say that Pn0 converges to F0, right?
Yes, sir.
As n converges to infinity. So but Pn0 is equal to 0. So therefore we can say F0 equal to 0. So you are done. Like so whenever whenever means if we can approximate a function by means of a limit of a odd polynomial, then it vanishes at 0. This was our reverse part. So now we will prove the forward part. So suppose f belongs to C01 means continuous function over 0 1 and f0 is equal to 0. Fine. Now we define another function g from minus o1 o1 to r by g of x is equal to fx whenever x belongs to 0 1 and minus f minus x whenever x belongs to minus 1 comma 1, sorry, minus 1 comma 0, right? Now see the, therefore gx, your function, you have a function g, your gx is equal to fx in 0 1, therefore it is continuous in this set. Also gx is continuous in gx is minus f minus x, so it is the composition of f and the function taking the negative of identity function. So f compose minus I actually. Therefore, this is also continuous. So therefore, we can say that this function g is continuous here as well as here, right? So can we say the function g is continuous on minus 1 comma 1? Continuous on minus 1 comma 1.
सर जीरो पे चेक करना होगा ना.
हाँ, 0 पे check करना होगा. तो is it necessary to check? We have some very famous result.
सर F00 होगा तभी कंटिन्यूस होगा.
हाँ, f0 तो 0 है. Assume f0 to be 0. Then तब अगर f0 equal to 0, it's given. Then how does it? It's continuous. ये continuous क्यों है? 100 साल पहले एक हवेली था. क्या क्या था? एक रिजल्ट था. कॉस्टिंग लिमा.
यस सर.
तब if is continuous here, continuous, sorry, g is continuous here, continuous there. Both are closed sets, and in the intersection they have the same value, right? Therefore your
GX
function
is
is
continuous.
continuous. G is
Yes.
continuous by Posting lemma. Huh? Actually, uh, these are very short tricks. So you have to use whenever you see some function is, and this is very useful. Okay. So now you have a function g, you have a continuous function g on minus 1 comma 1. Now you know something about Wester's approximation theorem or Stoneweister's approximation theorem, or you can say Stoneweister's theorem. So you have now you consider C minus 1 comma 1. Even see, sorry, no, okay, let me compare it here and then I'll tell you. Okay, so you have C minus 1 comma 1, right? And Stoneweister's theorem क्या बोलते हैं? इसको देखो. X be a compact topological space and A be an algebra of continuous real valued function. On X, separating the points of X and containing the constant function 1. Then this is dense in Cx. So this is the generalized version. But if we take X, the set X to be minus 1 comma 1. So this will be a compact set, and the version of Stoneweister's theorem will be looks like this one. So oh, this is again Dini. So I wrote something. Yeah, this one. Wester's theorem. So any continuous real valued function of R is the uniform limit of a sequence of polynomial. In fact, you can say that the polynomial function on minus 1 comma 1 is dense. Dense in C minus 1 comma 1. Okay. This is by Wester's theorem or Stoneweister's theorem. Clear? ये पता
Yes,
है?
sir.
ये पता है?
Yes, sir.
ये तो क्लास में पढ़ा था शायद. Okay. So therefore for this G, so now you have a function G here, and it is given that this is dense in C minus 1 comma 1. And what is our aim? We have assumed that F belongs to C01, and we want to prove that there is a sequence of odd polynomials. In other words, if we take say this B to be the collection of all odd collection of all odd polynomials, then we have to prove that this B closure is equal to, or we have to prove that there exists a sequence Pn subset of B script B such that this Pn minus F converges to 0. Or you can say, so this is the closure, or you have to prove that this B closure is actually set of all functions F such that, or in other words, you can say this is equal to F belongs to C 0 1 such that F0 is equal to 0. Okay, you have to prove this one. That's mean you have to prove that B closure is equal to this. That's mean if you take any point F from here, and if you take an epsilon neighborhood, okay, if you are able to find and see, if you take any point from here and take epsilon neighborhood of this one, means you are taking the set G belongs to, or say H belongs to C01 such that norm of H minus F less than epsilon. Okay, you consider this neighborhood. This is the epsilon neighborhood of F in C01. Okay, and to prove that this closure is equal to this, you have to prove that this intersection B is non-empty. Okay, so once you are able to prove this one, your result is done, right?
Yes, sir.
हाँ, so अभी क्या करना है? हाँ, अब हम क्या कहाँ पे हैं? Now we are in here. We are with G, which is continuous on C0, 1, and we also know that P minus 1, 1 is dense in C minus 1, 1. Now we have chosen one epsilon. Choose one epsilon, and since this is dense in here, so for this epsilon, for
We can take a sequence which converges to G.
we can take a sequence, but instead of taking sequence, this proving this one will be easier. Okay, because you know, right? So in a metric space, the closure point can be approximated by sequence.
Yes, sir.
Huh.
Sequential gradient.
Yeah. So now if we can prove that this closure is this one, then obviously for any point of here, you can find out a sequence, right? So actually, for this example or for this exercise, proving closure, proving that this part means B closure equal to this one, it's much more easier. So now choose epsilon greater than 0. So say that then for this epsilon, there exists a polynomial, say P belongs to P minus 1 comma 1 such that this norm G minus P infinite norm is less than epsilon. Fine. अब देखो, now P is a polynomial, right? So P can be expressed as say Px. You can say this is a0 plus a1x plus up to plus an x to the power n, right? अब देखो, now in Px there are even terms and even powers and odd powers, right? So write this as so a0. Now separate the even powers and odd powers. So a0 plus you can say a2x square plus a4x to the power 4 plus up to plus a say 2mx to the power 2m. Okay, and plus here a1x plus a3x cube plus up to a say 2k minus 1 x to the power 2k minus 1. Fine. You can write it down in this way, where either 2m is equal to n or 2k minus 1 is equal to n. We don't know, but given a polynomial, we can write down it as a sum of one odd polynomial and one even polynomial, right? Sorry, one
Yes, sir.
odd polynomial and one even polynomial. Now name this polynomial. So this odd one be our px. Sorry, this is our qx and this is our rx. Then q and r are all polynomials. Now our aim is to prove that these r, so these r can be approximated by f, means this r minus our f is less than epsilon. So this is our aim. Okay. So actually so far I have formulated the problem to get such a function or to get such a um, uh, odd
Sequence.
polynomial. Yes.
Sequence of odd polynomials.
Sequence of odd polynomial. Yes. So now you see. Huh. So now you can see that now gx. So what we have from here, this one. So what you know is that so gx minus you had px, right? This one, or you can say this g minus p infinity less than epsilon tha. So this implies mod gx minus px less than epsilon for all x belongs to 0 1. No, sorry, minus 1 comma 1, right? This
Yes, sir.
was our hypothesis. Now you see, look at gx minus px. Now take x from 0 comma 1, right?
So
When x
minus
belongs to huh?
0 से क्यों?
हाँ, नहीं एक्चुअली इसको अभी ब्रेक करेंगे, ब्रेक करके एक फॉर्मूलेटर करेंगे. रुको वन सेकेंड.
Okay.
हाँ. अभी अभी px क्या है? px इज qx माइनस rx. ओके, इसको भी लिख दिया. अब देखो, if x belongs to 0 1, जब x belongs to 0 1 तो अब gx क्या है? gx का वैल्यू, gx का वैल्यू fx. कहाँ पे कहाँ चला गया? हाँ, whenever x belongs to 0 1 gx is equal to fx, right?
Yes, sir.
gx is equal to fx, तो अभी क्या आ जाएगा, this is gx is equal to fx minus qx minus rx, right? And if x belongs to, again for x belongs to 0 1, if we take minus x, y equal to minus x, तब क्या होगा, तब क्या हो जाएगा, y belongs to minus 1 comma 1, right?
Yes, sir.
And this is still less than epsilon. Now see, y belongs to minus 1 comma 1, sorry, minus 1 comma 0. But for this also we have kya, we have gy minus qy minus ry less than epsilon by this result, by this
Yes.
result for all minus 1 comma 1. Now this simple, what does this implies? This implies g of minus x, sorry, g of y रहने दो. अभी जी वाई का मीनिंग क्या है, y बिलोंग्स टू माइनस 1 कमा 0, तो जी वाई का मतलब क्या है, माइनस एफ माइनस वाई, राइट?
Yes, sir.
हाँ, और क्यू वाई का ऐसे लिख दो, क्यू वाई मतलब माइनस एक्स माइनस आर ऑफ माइनस एक्स लेस देन एप्सिलॉन, राइट? अब देखो माइनस एफ माइनस वाई, सी माइनस एक्स इज इक्वल टू वाई, तो माइनस वाई मतलब क्या हो गया, एक्स, दिस इज एफ एक्स. अब देखो क्यू पे आ जाओ, व्हाट इज क्यू माइनस एक्स, you have q this one,
QX
then q minus x is equal to qx. And what is r minus x?
प्लस
यार
प्लस हो जाएगा.
नहीं, r minus x मतलब ये आगे माइनस आर एक्स हो जाएगा, नहीं?
हाँ सर, वहाँ पे
हाँ,
प्लस आ
आगे
जाएगा.
माइनस हो जाएगा और माइनस माइनस प्लस हो जाएगा, प्लस आर एक्स
यस
लेस
सर.
देन एप्सिलॉन. अभी इसको देखो एंड इसको देखो, अभी यू हैव दिस वन एंड यू हैव दिस वन, राइट? ठीक है, ये तो स्पेस नहीं है, इसमें कर देते हैं, यहाँ पे आगे थोड़ा बहुत जगह लेके. नाउ यू नीड fx minus rx. Now this can be written as fx plus, sorry, plus ये क्या है,
QX QX
वन सेकेंड, माइनस qx करेंगे या प्लस qx करेंगे, हाँ, प्लस qx माइनस rx माइनस qx, राइट? एक्चुअली इसको एक फॉर्मूला करके लिख सकते हैं, माइनस qx प्लस fx माइनस rx बाई 2. समझ में आया?
यस सर.
समझ में नहीं आया, ठीक है, फिर
आया
से
सर.
लिखता हूँ.
सर समझ में आ गया.
ठीक है, ठीक है, इसको ना लिखने दो पहले, इसको मत लिख सकते बाई 2 एंड 2 टाइम्स एफ एक्स माइनस
माइन
आर एक्स, राइट? हाँ, सो आप 2 टाइम्स मतलब आगे 1/2 कर दो, सो एफ एक्स माइनस आर एक्स प्लस क्यू एक्स माइनस क्यू एक्स कर दो, एंड 1 टाइम्स लिख दे एफ एक्स माइनस आर एक्स, यू हैव 1 मोर टाइम्स एफ एक्स माइनस आर एक्स, राइट? एंड सबके बाहर मॉड्यूलस.
सर
अभी
अब
देखो,
ट्रायंगल
हाँ, ट्राइंगल
एप्सिलॉन
देने
बाय
का,
2.
हाफ mod fx माइनस आर एक्स प्लस क्यू एक्स हो जाएगा प्लस एफ एक्स माइनस क्यू एक्स माइनस आर एक्स हो जाएगा, राइट? एंड दिस लेस देन एप्सिलॉन
एप्सिलॉन
प्लस एप्सिलॉन बाय 2 मतलब
2.
एप्सिलॉन. सो व्हाट यू हैव, mod fx
माइनस
माइनस आर एक्स लेस देन एप्सिलॉन फॉर ऑल एक्स, ओके, 0 1, क्योंकि यहाँ पे x f x any x था. Therefore, you can say mod f minus r less than epsilon with respect to supremum norm. Fine. तब हो गया
Yes,
एप्सिलॉन
sir.
नेबरहुड में एक r आ गया। r का r क्या है? एक ऑड पॉलिनोमियल, सो देयरफॉर इट्स क्लोजर इज दिस वन, सो प्रूव। फाइन।
Yes, sir.
हाँ, अभी ये जो सेकंड प्रॉब्लम है ये थोड़ा डिफिकल्ट है, तो बताओ इसे करूँ या छोड़ दूं? थोड़ा नहीं, ये बहुत ही डिफिकल्ट है। आई थॉट I'll do that during the sessions, but since no one is here, so if you want, I can solve it. Means, but it will take a lot of times. And you were saying you have exams also. So okay, okay. So before that, let me show this one. So ये पता है कि let X be a compact subset of R so that CX is separable metric space. How to prove this one? CX.
Sir, polynomials ले लेंगे with rational
हाँ
coefficients.
हाँ 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 हाँ। So polynomial with rational coefficients। फाइन। लेकिन इसको लिखना है अच्छी तरीके से, बस ऐसे ऐसे लिखोगे ना एग्जाम में तो 1 नंबर मिलेगा। ठीक है, मतलब इसको अच्छी तरीके से लिखना है। तो सी एक्स इज सेपरेबल, तो तुम्हें फर्स्ट फर्स्ट लेना है कि पॉलिनोमियल्स आर डेंस, एंड पॉलिनोमियल जब डेंस होगा तब हर एक पॉलिनोमियल के लिए तुमको एक रेशनल पॉलिनोमियल मिल जाएगा उसके उसके नेबरहुड में। तब इसको ऐसे करना है कि मतलब स्टेप लिखना है बहुत। हाँ, ये ऑब्जर्व कर सकते हो कि रेशनल पॉलिनोमियल्स विद रेशनल कोएफिशिएंट्स आर dense, but you need to work on this. On this means you cannot just trivially say it is dense. Polynomials are dense. So why the polynomials with rational coefficients are dense? This is important. Okay. तो अब इसको सॉल्व कर लेते हैं, है ना?
Okay, sir.
Okay. Yeah, you had exam
Sir,
one. हाँ
नहीं.
हाँ, क्या इसको सॉल्व करूँ या छोड़ दूँ?
Sir, जैसा आपको ठीक लगे.
ऐसा आपको ठीक लगे नहीं, अगर तुमको चाहिए तो, क्योंकि तुम अकेले अकेले हो ना क्लास में, और बाकी लोगों का तो जरूरत नहीं है।
करवा दो सर.
हाँ फाइन। अच्छा, लेकिन इसको ध्यान से समझना, ठीक है? ऐसा इस टाइप का एक क्वेश्चन आ भी सकता है एग्जाम में। ऐसे नहीं बोल सकते कि ये आएगा या दूसरा प्रॉब्लम, लेकिन पता नहीं, लेकिन इस टाइप का प्रॉब्लम यू विल फेस ड्यूरिंग योर मेजर एग्जाम। ओके, सो हियर, so what are the conditions of Stone-Oester's theorem first? So let us understand Stone-Oester's theorem first, and the statement means the statements are always very important. It says that if we have a compact topological space X and script A be an algebra of continuous real valued functions on X, and this collection separates the points of X, right? And this also contains the constant function. So first of all, this is an algebra of continuous function. This separates the points of X, and this collection contains the constant function, means one belongs to script A. Fine. Then, so Stone-Oester's theorem tells us that this collection will be dense in Cx. Fine. And these denseness happen with respect to the uniform metric. Now you come to this problem. You have similarly, you have an algebra of continuous real valued function, and you have a topological space X. So this is defined on the, means this script A is subset of Cx actually. And again, this separates points of X. You have to show that the closure, you have to show that this closure in Cx is either same or this one. Now tell me one thing, this problem consists of the arguments from Stone-Oester's theorem. But why we cannot apply Stone-Oester's theorem directly?
So constant function one नहीं.
हाँ, right, constant functions नहीं है, because one may not be descriptive. अगर ऐसा होता तो ये हो जाता है, ठीक है। अब ध्यान से समझना। सो सो इसको स्टार्ट करने से पहले थोड़ा बहुत वो कर लेते हैं। You know, say you suppose you have 0, 1 and you know root over x is continuous, right? Continuous on 0, 1, and you also know that there is a special kind of polynomials, or there is a special kind of functions which converges uniformly to this one. Namely, if you consider the sequence Pn of polynomials, of course, these are polynomials. How? Where your P1x is 0 and
Pn plus
Pn
omega.
plus 1x is given by what?
Pnx. Pnx
Pnx
minus 1 by 2.
minus या प्लस? प्लस है क्या कि माइनस है, क्या है? भूल गए हो? मुझे तो लगता है प्लस है। हाँ, माइनस नहीं है, ये प्लस है। लोग मैं देखता हूँ एलिप्रिंटस की बुक से, पेज नंबर 90। प्लस है, माइनस नहीं है। Pn यहाँ पे प्लस है, प्लस हाफ x माइनस Pn x स्क्वायर, ठीक है। This one. Can you
Okay.
tell me what is the difference between Pn x square and Pn square x? What is the difference? ये x है, ठीक है, ये भी x है। What is the difference between these two? This is actually what we do is that here we first fix this number x, okay, and therefore Pnx is a real number and its square. So actually, if whenever you are applying this Pnx, then it becomes a real number and you are taking square of a real number. Fine. Now see, your x runs over 0, 1. So it may happen that your Pnx become more than 1. So in that case, you will not apply again Pn, because the domain of definition of Pn is only 0, 1. That's why. So it's a different thing. Okay, it is not related to this problem. I just asked you. So whether it is clear. Anyway, okay. So now you see this converges uniformly to root x, right? This is what you know. So now this Pn's converges uniformly to root x. And you also can say that Pn, you also can say that P2 of 0 is P1 0 plus half 0 minus P1 0 square. Again 0, क्योंकि ये भी 0 है, ये भी 0 है. So therefore by inductive argument you can say that this Pn 0 is equal to 0 actually. Fine.
Yes, sir. Fine.
Now suppose you have a function belongs to, I am taking a function f from a closure. You know, when the script is an algebra, this implies this script A closure is also an algebra, right? You can prove it by using the sequence kind of arguments. Okay, I am assuming this one. So whenever it's an algebra, it's an algebra. It's an exercise. Okay, you must verify. Sorry. So now whenever f belongs to this and p is a polynomial, you can say that p and f. See, now I am considering this as a polynomial, not as a function. Okay, not as a polynomial function. Means say if your polynomial is say p n x is say a0 plus a1 x plus up to plus a n x to the power n, then I am considering, then of course what we have proved that a0 pgn0 is equal to 0 means a0 is equal to 0. So your polynomial will start from this one, right? This one. So now if we consider this function p, this function say a1 f plus a2 f square plus up to plus a n f to the power n. Here f square means f square x मतलब fx square, ठीक है? fx square, ठीक है? And say this function is your pnf. Fine. Now since your a closure is an algebra, you can say this implies pnf मतलब this function, this is again is a closure, right? So also you have f belongs to where a closure. So this implies norm of f infinity is finite. This is a finite number because all the continuous function of a compact set has an upper bound or it is a bounded. So it is finite, and in fact we can take it is positive by taking a non-zero function f whenever f not equal to 0. Okay. So then what we can say, if we consider now, you see your pnx converges uniformly to root over x. This function, can we say Pn f square by norm f0 square converges to mod f by norm f? Because it is just the root of this one,
Yes,
positive
sir.
root. Huh? And this implies, ये क्या imply करते हैं? This implies mod f belongs to script. Just multiply by norm f infinity, you will get mod f belongs to a closure, not a. Also, if we see this Pn of mod f, if we consider, it will converge to root over mod f. Because whenever mod f belongs to a closure, you have by the same argument, we will have Pn mod f belongs to a closure. So it will be a sequence of here. And since it's a closed set, you can say this converges to mod f uniformly, of course, with respect to uniform matrix. So therefore, you can say root of our mod f also belongs to a closure. Fine.
Yes, sir. Fine.
Now we will. So what we have proved, when f belongs to a closure, we have mod f and root of her mod f belongs to a closure. Actually, that's what I have proved so far. And we will use this one. Fine. Now assume that now you consider, suppose a closure not equal to this form. F belongs to Cx such that fa equal to 0. Suppose this is not of this form. तब क्या होगा? Then what is its converse argument? You can say for each say x or each y belongs to x, there exists a function, right? See, if for each y of x and if for if there is some y such that fy equal to 0 for all f, तब क्या होगा? तब ये करेक्शन ऐसा बन जाएगा ना, like, but this is not the case,
Yes, sir.
right? मतलब there exists a function f belongs to a closure such that f of y not equal to 0, right? Now you consider fy. You know some neighborhood property, right? Neighborhood property of real valued function. What is it? Fy not equal to 0. So you can consider a neighborhood, say fy minus epsilon 1 comma fy plus epsilon 1, where fy minus epsilon 1 is positive. Or say if it is, say, see, if fy is positive, we choose an epsilon 1 such that fy minus epsilon 1 is positive, and if fy is negative, we choose an epsilon 1 such that fy plus epsilon 1 is negative. Can we choose such epsilon 1?
Yes, sir.
We can always choose, right? So now you see, so what you can say now, if what if we take the what if we take this inverse? If we take f inverse of this one, does f assumes the value 0 over this interval? No, right?
No, sir.
The 0 here, 0 is not included in this set. Therefore, there is no z in this set, say S, means there does not exist z belongs to S such that fz equal to 0, right?
Yes, sir.
यहाँ पे कोई z नहीं है, right? No. Z belongs to S. If we take this one, because 0 is not here. Now, so what we can say, therefore, for each y belongs to say x, there exists fx belongs to a closure or fy belongs to a closure such that a closure and this neighborhood, right? This neighborhood corresponds y, and a neighborhood sy such that a neighborhood or open set such sy containing y such that fy of z not equal to 0 for all z belongs to sy. For each y you can find out. Now you see, can we write x as union of y belongs to y sy? Because each sy contains y.
Yes, sir.
Uh, you can write, now you have x is a compact set. What can we say then? There exists,
Finite subcover.
yes, a finite subcollection. Collection, say y1 up to yn, such that x is equal to union of I equal to 1 to n is yi, right? ये मिल गया. Now you define another function, say g1 on x to r by g1 of x is equal to fx1 square plus fx2 square plus up to fxn square. Fine. तब क्या बोल सकते हो? Now for each x, what you can say, x is the union of syi, and in syi this fxi, sorry, this will be fy. These fyis are non-zero. Therefore, their square is strictly positive. Therefore, we can say g1x is strictly positive for all x belongs to x. Clear?
Yes, sir.
Because for each x, x will contain in some syi, and for that syi, you will have fyi is non-zero, and therefore its square is positive. Fine. Now you have gx greater than 0. You also know this g1 is a continuous function on x, right? And real valued continuous function. You also know infimum of mod g1 exists, right? Because
Yes, sir.
g1 is a bound, means because its supremum and infimum exists. Now you consider the function gx to be g1x by infimum of g1x. So, or infimum of mod g1. G1, you can say g1x 0 less than equal to x less than equal to 1. As g1 is non-zero, so its infimum will be strictly positive. And therefore, what you can say, for each x, you have g1x greater than equal to its infimum, right? Therefore, you
Yes,
can say,
sir.
and it is a positive function. So you can say this is always strictly greater than 0. Right? Now, अब
Yes,
हम
sir.
क्या करेंगे? Using this g1, we will construct a sequence. We will construct a sequence from a closure which converges to 1. And since a closure is closed, therefore 1 will be in a closure. So what we will have?
Yes.
A closure is a algebra which separates the points of x, which contains the constant function. Therefore, by Stonewall's theorem, its closure is total
Dense.
Cx, right?
CX.
Yeah.
Yes,
Therefore,
sir.
A closure is dense, but A closure is closed, so therefore closure is A closure. So you will have Cx is equal to A closure. So this is the aim. So to prove such that, so now our aim is to prove 1 belongs to A closure actually. So for that we will consider now again you look at here, each of fy's, these are y, okay, these are y, y1, y2 up to yn. Now each of these fy's are from a closure, and a closure is an algebra, right? Therefore fyi close square belongs to a closure, this in a closure, and therefore and their finite sum is in a closure. That's mean
Yes, sir.
the function g1,
Z1
yes, this is belongs to
belongs
a
to A
closure.
closure.
Huh. Right? Now you consider, now we have learned something earlier, right? Whenever f belongs to a closure, its modulus belongs to a closure and its square root belongs to a closure, right? So what we can say, whenever you have g belongs to a closure, see, you had g1 belongs to a closure, but you did not had g belongs to a closure, but still g belongs to a closure because this is nothing but a scalar multiplication, right? We have multiplied g1 by a scalar.
Yes, sir.
Therefore g belongs to a closure अच्छा नहीं लग रहा है, पता है मुझे.
नहीं सर.
हाँ अभी हो गया
समझ.
बस बस 5 मिनट चाहिए और. Okay, now g belongs to a closure implies root of r mod g belongs to a closure, but g is a positive function, so you can say root of r g belongs to a closure. Okay, this is a closure. That's mean that is g power half belongs to a closure, right? Now g power half belongs to a closure implies g power half and iska root belongs to a closure. That's what we
Yes,
have
sir.
proved. And this इसका मतलब क्या है? G power 1 by 2 into 2 belongs to a closure, right? That's mean g power 1 by 2 square belongs to a closure. And g to the power 1 by 2 square belongs to a closure implies
G to the power 1 by 8 belongs to a closure.
g to the power 1 by 8 belongs to a closure. मतलब g to the power 1 by 2 cube belongs to a closure. So in a similar way, you can prove that g to the power 1 by 2 to the power n belongs to a closure. Right? Now this is a sequence. Now you have gx greater than 1 for all x. Say if x, and if you consider this sequence g to the power 1 by 2n, this sequence of function, you will see that g of 1 by 2n x is greater than g of 1 by 2m x for all x belongs to x, and whenever m is greater than n. ठीक है? जब m greater than n होगा तब g to the power 1 by 2n x is strictly greater than 1 by 2m x होगा, क्योंकि this value is always strictly greater than 1, है ना?
Yes.
जब जब 1 से बड़ा होता है तब हम जब उसका कोई स्क्वायर रूट लेते हैं तब वो छोटा हो जाता है, लेकिन जब 1 से
Yes.
छोटा होता है तब वो बड़ा हो जाता है ना? हाँ, तब देखो ये क्या है, ये सीक्वेंस ऑफ फंक्शंस, कंटिन्यूअस फंक्शन, सीक्वेंस ऑफ डिक्रीजिंग फंक्शंस, राइट? एंड व्हाट इज इट्स पॉइंट वाइज लिमिट? n tends to infinity g to the power 1 by 2n x. What is it? ये क्या है?
1.
हाँ, ये 1 है. Thank you. So this is 1, right? And this holds for each x. Therefore, if we consider say rx equal to 1, then what we can say? Oh, it is not rx. We can say just simply the constant function. This constant function, then g to the power 1 by 2n is a decreasing and converges to 1 pointwise. Right? Now you have something called Dini's result. What is Dini?
So if we have monotonically increasing sequence.
Increasing or decreasing? Anything is fine. We need
Yes,
a
sir. Yes.
monotone sequence.
Sequence.
Then if it converges pointwise, then it will
Then
converge
uniform.
uniformly, right?
Yes.
But your
Yes.
domain should be compact set. Therefore, what we can say, g to the power 1 by 2n, this sequence minus r, or simply write as 1, uniformly converges to 0. Right? Now g1
Yes.
by 2n belongs to a closure implies 1 belongs to a closure, because a closure is a closed set. Right? So now you have this collection. What? This is a separating family of continuous
Continuous function.
function number 2,
Containing
it's an
constant.
algebra, and number 3 contains 1. Right? तीन
Yes,
हो
sir.
गया. तब by Stone-Weierstrass
First.
theorem. You have a closure is equal to Cx. But a closure is closed. So a closure is simply a closure equal to Cx. Fine. हो गया प्रूफ.
Yes, sir.
आप इसको ध्यान से पढ़ना, ठीक है? अब अभी पता है कि इसमें प्रॉब्लम हो सकता है समझने में, तो ध्यान से पढ़ना हो जाएगा, नहीं इशू नहीं है, ठीक है? एंड अगर कोई प्रॉब्लम हो तो वो कर देना through MS Team, or through you can post in the topology group also. I will try to answer. Okay, fine.
Okay. Thank you, sir.
हाँ.